4, 3, 2, 1. Ok, Camila. ¿Listo? Pues empezamos. Bueno, buenas tardes a todos. Para mí es un placer estar aquí en esta charla de nuestro invitado internacional, Omar Richardson, a quien pues tuve la fortuna de conocer personalmente hace unos 4 años, cuando estuve haciendo una estancia doctoral en Suecia. Allí lo conocí mientras él era estudiante de doctorado. Entonces, bueno, Omar nos acompañó el año pasado en este coloquio, en la versión del año pasado, y pues es grato para nosotros contar con su presencia este año. Omar pues tiene un pregrado en matemáticas en la Universidad de Eindhoven, en Países Bajos, o lo que nosotros también conocemos como Holanda. También hizo allí un máster en matemáticas aplicadas, y recientemente, en mayo de este año, acabó su doctorado. Se graduó de doctor en matemáticas en la Universidad de Karlstad, en Suecia. Actualmente, Omar trabaja en una compañía en Noruega, específicamente en Oslo, que se llama Simula Consulting, los cuales hacen investigación y desarrollo tecnológico para compañías. Entonces, Omar nos va a hablar sobre unos temas de matemáticas aplicadas muy interesantes. Le agradezco pues su presencia, y pues Omar, puedes iniciar la charla. Omar, you can start now.
Thank you, Camila. All right, let me start by sharing my screen. Almost. Okay, I hope this is visible. I fear that if I make it completely full screen, it won't be clear anymore. Well, let's do it like this. Okay. So thank you, Camilo, and thank you to all the other organizers of this workshop as well. It's a pleasure and an honor for me to be here and to be able to talk about my work. So as Camila mentioned, I did my PhD. I finished it this year in May at Karlstad University in Sweden, under supervision of Professor Adrian Muntean, and since then I migrated to Norway to become a data scientist at Simula Consulting. So these days I'm mostly doing machine learning and scientific computing rather than analysis of partial differential equations, but the two subjects touch remarkably much if you go in deeper, which is quite nice. So today I will talk about the last work I did in my PhD studies, which deals with the analysis of partial differential equations and the implementation and evaluation of finite element schemes for those equations. Specifically, today I will talk about two-scale finite element systems, where two-scale is an instantiation of multiscale systems, which I will introduce shortly for all people not familiar with them. This work in particular is a joint work with my colleagues from the University of Sussex in Great Britain, Omar Lakkis and Chandrasekhar Venkataraman, as well as my ex-supervisor Adrian Muntean, who is at Karlstad University in Sweden. I would like to talk about a multiscale model. So, what is a multiscale model? There are a couple of similar but not equal definitions, and the one I will adhere to throughout this talk is a multiscale model being a mathematical model that utilizes different components that are defined on different time or length scales. So, the example I will be looking at are models that have two components. One the microscopic one and one macroscopic one, and a component here is a unit model. So this can be what I look at, a system of partial differential equations, but it could also be a network or an agent-based model. But here we're looking at compositions of partial differential equations, and multiscale models have become very popular over the last century and the beginning of the century in trying to model large space and time domains, as well as very complex phenomena that are hard to be tackled with a single scale model. So what can we see as an example? For instance, here we see the zoom in of the leaf of a plant, and you can discount the individual cells present. And here, if we zoom out, we see the plant, we see the leaf itself. If we're interested in describing the dynamics in transport of this plant, so imagine the transport of nutrients, the transport of liquids, we're going to run into trouble if we're looking to have one contiguous model that describes the flow. Imagine, for instance, that you zoom in to cell level and you describe a single cell and you describe all the organelles of the cell. Then you're running into a relatively complex geometry. These cells are small, the molecules are quite smaller, so you would get away with using some sort of PDE to establish exactly how these models how this liquid flows and how any concentration of nutrients and waste material within the liquid gets transported from perhaps one cell to another and within a cell. But if you would like to evaluate this transport on the level of the plant or even on the leaf of a plant, these very small elements of the individual cell will require a huge, very detailed resolution of your computational model, which in most cases leads to such a demand that it will be simply intractable to perform any kind of simulation. So there are many ways to circumvent this naive approach. One of them is to make suitable assumptions of homogeneity, but another one is to simply look at multiple layers within your model. One being what happens on cell level, so looking at all the constituents of a cell, looking at how the transport goes from one side to another perhaps, and instantiating another layer that can be seen as the macroscopic averaging or the macroscopic perspective of these cells. For instance, looking at the leaves and assuming some sort of average procedure of transport, and trying to couple these two together, which can in turn perform better than a simple macroscopic approach where you only consider the leaf, but much more efficient than considering each cell at any location within the leaf. So these multiscale frameworks, the multiscale framework that we will be talking about today, builds on heterogeneous multiscale methods that have been described before by, for instance, Björn Enquist or by Nagi and other people. But from a mathematical point of view, specifically, we're going to look at how we can represent microstructures with a varying geometry and distribute it over the macroscopic domain. These works are they've been described before by Igor Babushka, Ralph Showalter, and Todd Arbogast, for instance, others as well. And what we're interested here, the thing that we focus on and try to expand upon, is how can we computationally efficiently represent these varying microstructures, and having found a nice representation, how can we utilize the computational structure in such a way that we can distribute the work over multiple processors, or have a parallel implementation of this finite element scheme that we result in. So this work has been published, or it's been submitted for publishing a few months ago. It's still under review, but you can find it on archive. The link is here. With any interest, I can share a link to anyone who's interested at the end of the talk. The implementation of the finite element scheme is present on GitHub, and it's open source. So also that is available to anyone who would be interested. So what do I want to talk about? I would like to talk about today about the setup of this problem, discuss the well-posedness of our system of partial differential equations. So well-posedness here in the sense of Hadamard. We'll continue by constructing a finite element scheme for the system of equations. I will describe how such a scheme can be implemented, and highlight some of the details that might be interesting. And finally, I will talk a bit about how this implementation performed in our case. So we have some convergence benchmarks and some timing benchmarks which describe the parallelization aspects of this implementation. So let's start with the setting. I see that this becomes a bit small. Let me zoom out a bit so it's visible for every, so that everything is visible. Voilà. So let's start by describing the two-scale setting that we're in. We have a macroscopic domain, omega, that we see here on the left, and we use x as a variable that indexes this macroscopic domain. The boundary is given by partial omega, as you see here. And subsequently, for every point of x in this macroscopic domain, we instantiate a microscopic domain, capital Y of x, with the boundaries as you see here. We have a gamma ix, which denotes the inflow boundary, with a Robin boundary condition imposed on it. We have gamma ox, which denotes the outflow boundary, also Robin boundary condition. And then we have gamma n of x, which are Neumann boundary conditions, on which we have no flow. You see here that all of these are indexed with x, meaning that the shape of these domains and of these boundaries can vary with the location. It's important to note here that for each x we have a microscopic domain, but these microscopic domains don't see each other. There's no size relation between omega and y of x, so they are fully discoupled in terms to size, and they should be seen. This space should be seen in terms of an asymptotic expansion. Okay, so how can we mathematically describe these different microscopic geometries? Well, we use diffeomorphism zeta that takes a reference domain, a microscopic reference domain, and outputs for every position x in omega a microscopic domain y of x. And we will use this map, we will use this diffeomorphism to construct a finite element scheme that takes these deformations, as I can say, of this reference domain into account. that will help us later. We will later see also what assumptions we make on zeta in order to make this problem tractable in our setup. So here I present a system of equations. So we have three elliptic equations, two macroscopic ones in omega and one microscopic one. And we're trying to find u of x, v of x and y, so that's the microscopic one, and w of x satisfying the following equations. So I would like to, so these are just the bulk equations. I will show the boundary conditions on the next slide in order to make sure it's still a bit legible. I think the interesting aspects of this system are that there is a conservation of mass. It's not clear now, but you see that there is a right-hand side in which there is an inflow coming from gamma I of x and an outflow of gamma O of x in the right-hand side of the W equation. We'll see that appearing in the microscopic system on the next slide. These equations are linear, so their analysis is relatively simple, which allows us to fully focus on the setup of the multiscale finite element framework. But the framework here still allows us enough space to hopefully build more realistic behavior later on. But I would like to remark that these equations are mostly toy models. They are mostly here to establish how we can really use these varying microstructures in a finite element setup. Okay, so here we see the boundary conditions, quite standard, I would say. So we have the Dirichlet boundary conditions on U, Dirichlet and Neumann. We have inflow and outflow boundary conditions on microscopic domain V. Sorry, for microscopic equation V, and only Neumann conditions for W. So, having completed this picture, what we're trying to model here is the transport of and the creation of a certain constituent W. W here is initially 0. And its only creation comes from the microscopic V, which in turn gets created from U. And on U, we have a certain inflow, an infinite reservoir that comes from the Dirichlet boundary condition. And the phenomenon that we're trying to model here is exactly the transport of nutrients in leaves. Exactly the example that we discussed earlier. So this is an example of Auxin transport, and what these constituents mean is, well, we basically have a source of minerals and water, U, that flows in on one side into the leaf, into the stem somewhere, and these constituents are then converted in the cell microscopically in V to create W, and this W is then globally present and gets transported macroscopically within the leaf. So here we see that the cells individually are responsible for the creation of nutrients, and those are spread macroscopically. And here we only have inflow and outflow terms, so we're curious to see how the shape and the location of the cells affects this distribution of this desired W. And we will see that a little bit later. So, although we don't focus on the analysis of the system of PDE here, it's a relatively easy to handle system. So it's certain quite natural assumptions on the data and the parameters, you can show that there is a unique weak solution to this problem in the below function spaces with regularity that one might expect. So H1 on U, H1 on V microscopically, and L2 macroscopically, so in the X variable, and H1 on for WH1 omega as well. I think the most interesting assumptions here are the ones that are presented from on kappa 1 to kappa 4, and these parameters define the inflow and the outflow rates of U, V, and W. So these rates would need to be physical in order for the problem to be stable. This is a sufficient condition, not a necessary one. These two, actually all of them. The other interesting assumption is the one that we have to make on the diffeomorphism that creates the geometry of the microscopic structures. So we see here that if we compute the determinant of the Jacobian of this diffeomorphism, it should be bounded from above and below so that we can compute an inverse. And also, we want this inverse of this diffeomorphism to be smooth. Again, this is a sufficient condition that allows us to manipulate the pushback and the pull forward of the microscopic equation onto different domains. Okay, let's move on to the finite element formulation. Well, if we construct different spaces, so as you've seen, our microscopic function V is defined on both omega and y of x. So its finite element approximation will be an approximation which is discretized in both omega and y of x. And here you see what these function spaces look like. So we take a positive macroscopic mesh parameter capital H and the microscopic mesh parameter H, and use that to construct we use it to construct a finite element space consisting of splines, linear splines, where for U of H we also impose that any function there has to be 0 on the Dirichlet boundary condition, just to simplify matters. So basically, here we go. We have our approximation of the following structure. So we have basis functions psi that span U of capital H, and basis functions eta that span V of H. And we see that these microscopic functions, this V of x and y, we assume that they can be represented by a tensor product of the microscopic and the microscopic space. And also we see here that this map comes in. So what we do, rather than constructing a different basis for each y of x, we simply construct a basis for the reference domain Z and use the mapping here, a discretized mapping where zeta I indicates the exact zoom in of the macroscopic domain, and we use a composition to express our microscopic function on this deformed microscopic domain. Okay, so this leads us to a relatively standard discrete weak form. I won't go into much detail on this, but what I would like to show here is the discretization of this microscopic term, because that's the only one that's out of the ordinary, that's non-trivial. So what one can do is, using this mapping, you can compute the inverse of the Jacobian, well, let's call that K, and we can compute the determinant of the Jacobian, let's call that J. And by using relatively basic calculus techniques, you can transform the finite element formulation from the warped domain y of x to the reference domain z. And by so all you would have to deal with are the transformations, and these are given by in fact this correction vector k transpose j, which also becomes very relevant in the implementation itself. So let me move on to the core, or at least the result part of the talk. So if you have all of these materials, if you have all of these techniques, what can you do with them? Well, we've used them to implement a slightly so an Eve implementation of this would have to require a different microscopic structure for each, but we're going to use all of these techniques to now make sure that we can construct and do all of our microscopic computations on only the reference domain Z. So this implementation is done in DL2. DL2 is a finite element library in C++. That facilitates the creation of simulations of partial differential equations. It is relatively low level, which allows the creation of all kinds of custom data structures and different routines. So our implementation, which uses DL2, and extend it a little bit with things that we would need in order to use multiscale function objects. It's on GitHub, as I mentioned, and for these extensions we built multiscale functions and multiscale tensors to take care of the assembly. And because this mapping makes it rather difficult to construct systems that can be used for testing and benchmarking the system of PDE, we added a Python module. We added a Python script, better said, based on SymPy, the symbolic Python library, that allows the prescription of a set of solutions, a set of desired solutions. So a proposed u of x, v of x and y, and w of x, and a certain mapping, zeta of x and y, and uses this to compute all the data and parameters in the system. So it outputs. So it uses the prescribed solution. It constructs data. It outputs that to a parameter file that DL2 can read, so that it becomes rather trivial then to simply take this file and to run it and see if the expected behavior of this system is as it should be, allowing for the quick markup of performance benchmarks and the like. So also this is it's bundled with the implementation, so that's available as well. So how do we go about solving a system like this? What we've done here is decoupling the system into the macroscopic and the microscopic part. And so it's in a sense it's a Picard iteration scheme. We solve the macroscopic parts with the microscopic data fixed from a previous iteration or an initial iteration, or initial guess. We use that, and we use the resulting macroscopic functions u and w, or the function approximations, to iterate over the microscopic data. And this microscopic data now is a bunch of computations that are all done over the same reference domain. And because it's over the same reference domain, we can use we can use the same computational structures and get quite a speed up in computation compared to the naive approach of having all kinds of different microscopic domains. So we use the method of manufactured solutions in conjunction with the SymPy module that I mentioned earlier to create a set of different systems. And here we see that for this implementation that it works. So we have expected convergence of errors. I didn't in this talk discuss exactly what can be expected of two-scale finite element systems. We have some similar research on time-dependent and and stationary and time systems, which is presented in my PhD thesis. So for anyone who's interested, I can share any reference to that as well. It's available online. But based on those slightly different situations, I must add, we get the convergence results that we expect. So second order in the L2 norm, both microscopically and macroscopically, and first order convergence in the H1 norm. And you see that especially in the H1 norm that there is a bit of a magnitude difference. This has to do with the fact that if you integrate over these systems, there is no intrinsic, because there's no size relation, there is no intrinsic relation between errors either. So that is something to take into account when you look at errors and you rescale them, what kind of units you're working with. I must say that as an applied mathematician, and that was definitely not a biologist, I've let most of that pass me by, but I think that's rather important if you're trying to use a multiscale model in practice. Okay, so here I think we can see the effect of these varying microstructures themselves on the distribution of W. So what we see here are two separate situations, and we show the W and the V, and we see it in the above situation. So the above plots, we see a W and a V, and the mapping chosen here is the identity mapping, the diffeomorphism zeta. This leads to the fact that all the microscopic domains have the same size and shape, and that leads to a rather symmetric profile, as you can see in both the V and the W on the left. Now, we've done something slightly different in the below case, where the mapping is such that the shapes are presented, that it leads to the shapes presented in V, which is, you can see two things here. So mostly that there's a certain difference in size ratio going from up to down. What I was going for initially was mimicking the topology of plant cells, so making them a little bit more thick in the middle and more stretched out at the edges, like plant cells would be in a stem. But that's a fully symmetric situation, so then you get still fully symmetric results. So in order to play with that a little bit more here, I have a slight asymmetry introduced here, and you can see that it has quite a strong effect on the distribution of W. So this makes the case that varying microstructures can impact the evolution, can impact the modeling of the evolution quite a lot. Okay, finally I would like to say a couple of words on the parallelization approach. So for the parallelization of solving linear systems, but more specifically of solving finite element systems, there are a couple of standard approaches, and mostly what the options one has is to choose between a shared memory approach and a distributed memory approach, where a shared memory approach basically means that you have a computing unit, well, let's say let's say we have a machine, and this machine has several computing units, and each of these computing units has access to one bucket of memory, so they can deposit values there, retrieve values from there. So this is rather different from the setup where you have a distributed memory approach, where you have a machine, or perhaps even multiple machines, where CPU units only have access to their own memory, and they explicitly have to lay links over a certain network, be it inside the machine or to actual different machines, but they explicitly have to exchange values with other processing units, with other CPU units. Here we opted for a shared memory parallelization. This is a start. Our investigation in this section is not finished yet, and we have some ideas on how to extend this to a hybrid approach where we take both shared memory parallelization and distributed into account. But here we start off with a shared memory approach, where we what we do is whenever we have our microscopic contributions, when we're constructing our assembly is the biggest step here. The assembly of the linear matrix that will reflect that will solve to find the coefficients of the finite element function approximation. So for this assembly, we loop over each cell in the microscope, in all microscopic systems, which are now all identical, and we distribute the tasks to assemble this over all the processing units available. And like this, we loop over each cell until all the cells are complete, and then the solving itself, which is rather trivial to parallelize, is also distributed over multiple cells. But although important, it's a little bit less interesting step. Okay, so actually the performance of this parallelization varies strongly with how the system is set up. So one can imagine, this is something that I didn't discuss in depth, but let's go back quickly to see here this domain. So the way we discretize this within is that we only compute a finite number of microscopic systems. So we zoom in at certain points in the domain, and for each zoom in, we instantiate the microscopic system. And each zoom in coincides for our finite element scheme with a support point of, or well, let's say sloppily, with a degree of freedom, roughly a degree of freedom on the macroscopic domain that allows us to interpolate over the values that come back from this microscopic domain with standard finite element tools. Then we also discretize the Y domain in a standard manner, so to whatever resolution we like, with mesh size small h. But this leaves us some options. If we're interested in a certain resolution, we can, for instance, choose to only sample quite coarsely from the macroscopic domain and more finely, relatively, from the microscopic domain, so that we have a small mesh here and a small mesh size here and a large mesh size there. Or we could do the opposite. It depends a bit on which level you're more interested in. So the opposite would be to sample finely here and therefore instantiate a whole bunch of microscopic domains, each of them having a coarse mesh. And this affects the parallelization in this shared memory approach, because it turns out that if you have only a coarse macroscopic mesh and a few number of microscopic systems, each of them indexed quite finely, then this parallelization approach works wonders. You see that the speed up for more and more threads behaves almost perfectly, at least up until 28, which is a mark I will come to later. And you see that the walk lock time goes down inversely quite nicely, as if this would almost make you believe that you could keep doing this infinitely, which I can tell you now you can't. for multiple reasons. But the algorithm, the parallelization algorithm, works quite well in this case. Whereas if you turn that around, so you have a very fine macroscopic mesh with very coarse microscopic systems, you have an initial reduction, of course, but then the performance starts to not increase that much extra anymore. You see that both here and here. The speed up increases, well, very little. This has to do with the fact that if you have very many microscopic domains, even if they're the same, you still need to construct all these solution vectors, and the overhead in switching from one vector to another becomes too big, and you see that starts be detrimental to the performance. So this has been tested on two HPC clusters, on Kebnekaise, which is a supercomputer in Luleå, Sweden, and on the Apollo 2, which is a high-performance cluster in the university from the University of Sussex in the UK. The issue here is that it's much more common to encounter large systems with a distributed memory approach, because it's in hardware it doesn't scale super well to have different computing units, more and more computing units in the same shared memory. Those systems exist up to more than 20. So the best system. These results were trained on 28 cores that shared the same memory. This was tough to find. Their bigger system exists up to 50, 100, and I guess even more than that. But they start to become inclusive, whereas distributed memories is much easier to come by. So it would be quite valuable for a scientific computing approach to introduce also a distributed approach to this, and that's something that we'll be working on in the future. Other things that we'll be working on is trying to extend this system to a time-dependent one, so not working on elliptic equations but on parabolic equations, and seeing if we can somehow work with domains that are varying in time, but that will be a challenge. But that will be, I think, a nice extension of the thing that we're working on right now. Although, well, we haven't gotten started on it yet. Another thing that would be a nice addition would be mesh refinement approaches. So establishing a posteriori error estimates and use them to locally refine meshes in such a way that it doesn't destroy the synergy that we have in the microscopic systems. Thank you very much for your attention, and with this I would like to open the floor for questions.
Okay, Omar, thank you very much for your time, and thank you very much for this nice presentation. So we will move to some questions of the audience. Quisiéramos saber si alguien tiene dudas o preguntas que le quiera hacer a Omar. Las estaremos leyendo en el chat de YouTube. It seems that we don't have questions, Omar. Parece que no tenemos preguntas de la audiencia. Entonces, te agradecemos. Thank you very much again. And we will see you soon. I hopefully for the next year version of this colloquium.
That would be very nice. Yes. Well, thank you very much, Camilo. It was really nice to be able to speak here, and yeah, good luck.
Thank you, man.